Good evening, ladies and gentlemen. How's everyone tonight? Pretty good? Good. All right. Again, my name is Mark Razzie. I'm from the Public Services Office. I want to thank you all for joining us tonight. I hope you continue to do so. Shall we? JPL has always been involved in propulsion research and development. After all, it's in our name. But over the years, we've transitioned from liquid-fueled rocket motors to more exotic fare, like ion propulsion. JPL's dawn mission to the main belt asteroids Vesta and Ceres is using this technology for its long-duration cruise to these bodies, reaching Vesta in August of 2011 and Ceres on February 1st, 2015. A mission like this would be impossible with any other type of propulsion technology, and similar thrusters are being used by a number of communication satellites to control their orbits around Earth. Tonight's speaker is an expert in this technology. He received his PhD in applied plasma physics from UCLA in 1981, and after a 5-year stint at HRL Hughes Boeing and patenting numerous technologies and founding a company, he came to JPL in 2003 as a senior research scientist. There he develops electric propulsion systems for deep space probes and satellites. He is an expert in ion and Hall thrusters, ion beams, satellite communication, high voltage power modulator technology, and the modification of materials by plasmas. He also finds time to teach wireless communications at USC and spacecraft design right across town at UCLA. Not to mention that he is a senior research fellow of the Institute of Electrical and Electronics Engineers, an associate fellow of the American Institute of Aeronautics and Astronautics, and a lifetime member of the American Physical Society. He has many designs, and his many designs and inventions include microwave amplifiers used by satellite radio, and the plasma deposition machine that is used to make sunglasses. He has published more than 100 refereed journal articles, dozens of conference papers, presented at more IEEE and APS conferences than he can remember, and is currently working on his second book. So needless to say, he's a pretty busy fellow, and we're happy he could join us tonight. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Dan Goebel.
Thank you, Mark. Well, good evening. I was a little bit concerned about coming to this and starting with a Star Trek reference. For those of you in the audience who were born after 1965 or your parents don't let you see internet, this certainly is Star Trek. It's impulse power, Scotty. And the reason for bringing this up is I was trying to think, what is advanced propulsion? How do I explain it? And one of the things is it's propulsion that's done in the future or going to be futuristic. And the one thing that I know is Captain Kirk never said, ever, chemical rockets, Scotty. Not done. What he said was impulse power. Impulse is thrust, and power, as far as I'm concerned, is electricity. So this is electrical propulsion, and that's what I do. So this is what we're going to talk about. I'm going to give you a little bit of history in getting there, which is talking about where we are in chemical propulsion, and then transition to this newer advanced technology. But before I start, I've got to tell you a little bit. I was really worried a couple of days ago because I learned that the people who came and gave this talk last month showed up in Elizabethan costumes, right? And I thought, oh my God, do I have to dress as Scotty, or somebody to get any credibility? And I was really worried about this because, you see, my wife is on travel, she's out of the state, and my daughter's away at college, so there was nobody to tell me how to dress. And so I was really worried, and what do you do in that case? You go to the internet, and you do research. And my research was to download previous webcasts of this talk and find out what people were wearing, right? That's important so that I have a good impression. And what I found was that if I was a university professor, especially from Cornell or back east somewhere, it's blue jeans, shirt, and a tweed jacket, right? If I was in upper JPL management, it's a tie. If I'm a JPL scientist, it's like a polo shirt and probably pants that aren't quite long enough. And all of those are candidates. I could do them all. And so I did the only thing that a man really could do. I went and got a haircut. So I'm hoping that this this will be acceptable to everyone. Now, we're going to talk about propulsion. And the first thing you think about in propulsion is a chemical propulsion. And so you've got to start a propulsion talk with looking at a shuttle launch. And this is because it's incredibly impressive.
Onboard fuel cells. Coming up on a go for auto sequence start.
I guess shuttle launches take a long time.
And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 9, 8, 7, 6, go for main engine start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Houston now controlling the flight of Discovery. The space shuttle begins the journey back into orbit. Discovery completes its roll. The shuttle now heads down wings level for the 8.5-meter flight to orbit. This view from a camera on the external tanks of liquid oxygen feed line showing the bird's eye view of Discovery as it races.
All right. Well, that's propulsion, right? Well, tonight I'm going to talk about some other types of propulsion. And of course, we just looked at launch rockets. That's chemical propulsion in a big way. But I'm going to talk a little bit about other types of chemical propulsion, which are like boost rockets. If you go into orbit and you want to deorbit, for example, you're going to the moon or you're trying to boost yourself out into the solar system, they have smaller rockets that are used for that. There's chemical rockets that are used for descending, like onto the moon or onto Mars, or launching off of a surface, ascent, descent rockets. And even control rockets. You've got to point your satellite, you've got to make sure it's going in the right direction, and they have control rockets, reaction control systems. So that's a type of chemical rocket. And then I'm also going to talk about electric propulsion. And here you see an ion thruster operating in the laboratory, and we'll give you a little bit of an idea about how those work. So there's a warning about this. Now, if you're going to talk propulsion, you have to learn 2 new words. And so I'm just warning you right now, you're going to become experts in this. The first, so that you know what I'm talking about. The first one I'm going to talk about is ISP, and that stands for specific impulse. And don't be confused, because what that is miles per gallon. How much thrust do you get for a given amount of fuel that you're taking up into space? How many miles per gallon is your rocket system working? So when I talk about ISP, I'm talking about how far am I going to get with a given amount of fuel that I'm taking along. And the second one that I have to use to talk about propulsion is called delta V. And delta V is a change in velocity. Now, the reason that this is important is that when you actually do propulsion and you're going out into the solar system or you're going somewhere, you don't just take a straight shot and head for Mars. Because of the pull of the sun, everything in the solar system works on orbits. And so you actually don't go directly to Mars. What you do is you change your orbit, and you run on an orbit that intersects Mars. The amount of velocity change to change your orbit is fixed by your mission. If you're going to Mars, it's a certain kilometers per second. If you're going to Saturn, it's a certain kilometers per second. It's just how much more velocity does your spacecraft have to have this larger orbit to go further and further out into the solar system. So those are your 2 terms, miles per gallon and delta V. And those will be important when we're evaluating how good are our rockets as we go forward. Now, I'm going to start off with chemical propulsion, and it's kind of fun to just do the old pictures because this is one of the first pictures. JPL was a pioneer in liquid rocket motor tests. This was one of the first ones done in 1936 in the Arroyo right over here by some students of Caltech under the supervision of von Karman. This is the von Karman lecture series. Von Karman was actually not that much into rockets, but he had some students who wanted to be, and he let them, and so they went into the Arroyo and started these types of tests. And one of the fun things about this test is you can see at the bottom there's some sandbags there. My understanding is that the people doing the test were behind the sandbags that way. Stay out of trouble because these things do blow up. Why is this jet propulsion laboratory? Well, von Karman and the people who were doing rocket propulsion, of course, were looking for financial support. And during World War II, the Army wanted them not to so much do rockets as much as do jet-assisted takeoff for carriers, for small runways, those types of things. And so they actually funded von Karman and the group here to start jet propulsion, assisted propulsion, and that's led to the founding of JPL. The first jet-assisted takeoff tests were done at March Air Force Base right here in Riverside. This is 1941, and they did this for pretty much most of the duration of the war. But they also were working very much on missiles for the Army. This is a photograph of, well, the first one they did was an 8-foot-long rocket they called Private A. Only went 11 miles, but that was in 1944. And later on that year, they did the 16-foot-long WAC Corporal, which is the one that you see there. It made it to 250,000 feet, so that's a real rocket. That's really doing great. And sometime after that, they actually put it on as a second stage to a V2 rocket that they rebuilt from the drawings that they got from the Germans. And it made it to 244 miles, which is the transition into space. So the JPL actually flew the first US rocket that ever made it into space right after the war. Now, propulsion back then was what I call a dirty business, and this is a good example of that. As you see some of the technicians standing around in their coveralls, and they must have been very much involved in it because they look pretty dirty. And the fun thing about this is you see their pants, or their coveralls are actually tattered, and one of the reasons for that is that part of the chemical fuels that they used back then in these rockets included nitric acid, which they probably were splashed on, and the nitric acid kind of ate it away. So if you were in rocket propulsion back in the 40s, you really wanted to be. It was a place that you liked because it was pretty dirty. JPL was really known after the war for solid rocket propulsion, and this is one of the first examples of that. It's called the Thunderbird. It was the first to use a polysulfide fuel, which is a type of solid rocket fuel that was very prevalent in the late 40s and into the 50s. And it was done in 1947. This is one of the first tests. It looks like kind of a small rocket, but it turned into larger rockets later on. And then through the 50s, they did a lot of testing of different types of rocket technologies and rocket motors right here on laboratory at JPL. And this is an example in a block room here of a rocket motor that's being set up. And this was an article in a Saturday Evening Post in 1955 about how the rocket screamed and the whole blockhouse shook and there was noise and vibration. Chemical propulsion is kind of fun like that, right? It's very, very interesting. And the reason I really like this picture is I'm really sure that that blockhouse is my laboratory right now that I use for electric propulsion. So maybe we'll see a picture of that later, and you'll kind of recognize some of that. And they kind of kept doing this work in the 1950s. This is an example. The rockets got so large that they couldn't do them in the lab, and they couldn't do them in the Arroyo. So they actually took them out to Edwards Air Force Base out in the Mojave area and started running these very large engines. This is the Corporal E with a thrust of 100,000 pounds. And it was really used one of the first anti-aircraft rockets, missile rockets. Now, this was actually part of the reasons that JPL stopped doing rocket work because it was so hard to do in this facility. You know, pretty soon Lockheed Yada gets pretty upset about rockets going off in the neighborhood. And so in the 50s, there was a transition of saying, if we're going to continue to do rockets, we need to do it somewhere else. They did it at Edwards. Everyone complained about having to drive out there and all those types of things. And so JPL kind of thought, maybe we ought to move up a little bit in the food chain. And moving up in the food chain means that now what we're going to do is build satellites instead of building rockets. And so you've all seen the response to Sputnik, of course, was the development of the Explorer 1 spacecraft. We also built some of the rocketry for that, but primarily the satellite itself, and further on, all the satellites that have been built here through the 50s and 60s, late 50s and into the 60s and 70s. So JPL kind of got out of the business of really doing big rockets in about 1958 or so, but they didn't completely stop. They still do what's called specialty chemical propulsion, and what that means is that they might buy the rocket from somebody else, but they figure out how it goes onto the spacecraft and the plumbing and the control that's involved. And this is an example of the rovers. I think just a couple of months ago you saw perhaps a rover talk of the vehicles that are on Mars right now. And it turns out that the top picture here is actually the spacecraft before it was launched, and on the top of that is the descent vehicle. You can see the gold circle is a fuel tank for chemical propulsion. And on the right, how this really worked is that they had a parachute that brought it into the Martian atmosphere. And some distance above the surface, they had these retro rockets fire. And it actually stopped the descent, and it hovered. And then they dropped the rover inside of an airbag, and it bounced to a stop. And so that whole design of that descent stage and those retro rockets in order to do that job was done here at JPL. They still do that now. The next Mars rover is called the Mars Science Laboratory, MSL. It's due to launch in 2011. And they're doing the same kind of a thing. They actually have a descent stage, which you see in the picture there. It's going to go into the atmosphere of Mars, come down to some level, and then hover. And the problem is that the Mars Science Lab is too large to actually drop in an airbag. It's just too big. It's the same size as a Mini Cooper, and it would just break an airbag. And so what they're going to do now is from this hovering platform, they're actually going to use a crane, and they're actually going to drop the rover, well, not drop, I hope, let the rover down softly and set it down on the surface from a hovering platform. Well, that's not only got all these chemical rockets that you see here, which they designed and did the implementation here at JPL, but also the control system for that. Because you can imagine you don't want this platform moving around in the wind and shaking as you're trying to let this very expensive rover down. And so all the control rocketry is done here at JPL to make sure that we have a stable platform. So there's still a lot of work on chemical propulsion here at JPL, but it's specialty. It's really the controls and the special things that you wouldn't get somewhere else. It certainly is not launch vehicles. So now we're going to talk about advanced propulsion, or what's the next step. What are the things that we still do here at JPL? And you guys remember ISP, it's miles per gallon, right? The way to get more miles per gallon from rocket fuel is to increase the velocity of the particles that are coming out. If you do the math, what you find is that ISP is actually directly proportional to the velocity of the particles. Now what happens in a chemical rocket is you're burning propellants, right? So there's molecules in there, and when you burn them, you break these molecules. The velocity of the particles that come out is the chemical bond of those molecules, and that's all you can get. So it isn't like you can get 1,000,000 miles an hour out of breaking these bonds. It's a finite velocity. It's 5 kilometers a second or whatever the number is, and it's just associated with the chemistry. So the only way you're going to get higher velocity particles is to use a different way to accelerate them, and we use electricity. So the idea is now what we're going to do is we're going to either heat this propellant up with electricity, or we're even going to accelerate the particles with electricity and get more velocity. We get more velocity, we get more miles per gallon, more ISP. So that's the concept. By the way, that concept was started in 1906 by Goddard. It's been around for a while. And so that tells you kind of what the benefit is. Now, why is this good? Why do we want more miles per gallon? If you look at chemical propulsion, you have to take a lot of chemical fuel with you to do things. In other words, the miles per gallon is not very good. And so what you find is that a chemical rocket system is really big, mostly because it's carrying a lot of fuel. And the payload, what you're taking, which is scientific instruments or communication communication channels or cameras, whatever you're trying to take and do science with or do communication with, that's small compared to the size of the rockets. And my analogy of that is that this is the Hummer of the spacecraft world. Yeah, it's big, and it's got a lot of power and a lot of thrust, but it's a pretty poor gas mileage. Now, electric propulsion is the opposite. Electric propulsion has a high ISP, which means you can take the same amount of payload and you can deliver it with a smaller amount of fuel. So the whole spacecraft gets smaller. And so this looks like a Prius, that's a good example because that's electricity anyway. But the whole idea of a Prius is that you have a high miles per gallon and you have less fuel, and that makes it literally a lot cheaper and a lot smaller. So you can use electric propulsion to actually reduce the cost of your spacecraft, make it smaller, make it more manageable. One of the things that I want to tell you is that there are some places where a Prius can't go, and you have to have a Hummer, right? You just need that horsepower, you need that force. So there are chemical missions out there that you just want to do because you need all that thrust. On the other hand, Priuses can go in a lot of places. And so there's lots of opportunities to go and say, rather than drive my Hummer to Mars, I'm going to drive my Prius, and I'm going to have a much smaller launch vehicle and save a lot of money. Now, saving money is one thing, but here's the only equation you're going to get tonight, which is what's called the rocket equation, derived in 1911 in Russia. It's been around for a while. But if you look at the rocket equation, the amount of mass that you're sending somewhere, so how much payload we're going to send to Mars or to send to Saturn, is equal to how much you start with in your rocket times this e to the delta v over the ISP. So now you guys know your terms. Delta v is this velocity change in order to change the orbit to get there. So if you have a higher ISP, if you have more miles per gallon, you plug it into this equation, you deliver more mass. And so electric propulsion gives you the possibility for the same size rocket to deliver a lot more payload. And that's really great if you want to deliver more science, you want to deliver bigger rovers, you want to do more communication channels in your communication satellites. Electric propulsion gives you that option because you're not wasting all that mass on fuel, you're using it on payload. So that's the benefit of electric propulsion, ion propulsion. Now, earlier on, you just heard the mention of Dawn. Dawn is a spacecraft right now that's flying using ion propulsion, electric propulsion. And of course, it was launched on a launch vehicle called a Delta II Heavy. And the launch vehicle is 40 meters high. It weighs 230,000 kilograms. And it has this huge thrust, 140,000 pounds of thrust. The ion propulsion system, once you're in space, you have an ion propulsion system, is that big down here. It's this little guy down here. It's a tank about this big and a propulsion system that's about this big. So it's 2 meters high, weighs about 1,000 pounds, 500 kilograms, and it has a thrust of 0.3 ounces. That's the thrust of a piece of paper. And I'm going to tell you that's okay. It's not much thrust, but you'll see in a minute that it still works. So the ion propulsion system, actually the propellant tank that's down there would actually fit in the trunk of your car. It's about like this, holds about 1,000 pounds of xenon. It's the gas that we use as the propellant. And it's very small compared to this spacecraft, but the delta V given to this launch vehicle, the delta V given to the spacecraft by the launch vehicle is the same as the delta V given by this little tiny electric propulsion system because we're using electricity. So there's a great advantage in using electricity for these jobs. Now, I already talked about Scotty and how we saw things in Star Trek, but we've been thinking about this for a long time. Those of you who remember 2001, I love this, because 2001, that's what the spacecraft looked like on the left side. It's a little dark here. But when you saw that view at the end and it was going away, those were blue glows back there. Those were ion sources, ion engines, just like we're using now for Dawn. So even back in the middle 60s, we knew about ion thrusters and ion engines and the benefits of using electric propulsion. And Hollywood was way ahead of us, and they were already showing what's going to happen in the future. The future turned out to be only a few years ago, because in about 2004, 2005, NASA started a program called Prometheus. I don't know if you heard about that, but the idea is we want to go to deep space, in this case to Jupiter and to Saturn, and what they were going to do is use nuclear power, fly large nuclear power systems, and use that to power ion thrusters, ion engines, and go to Jupiter. So the concepts from the 60s actually turned into the designs of the 21st century, and we made designs for this, and I'm going to actually show you one of these ion engines a little bit later. So we are making progress towards this vision of using ion propulsion, impulse power, to get to the outer reaches of the solar system. All right. Now, we're talking about electric power, and it's very interesting to talk about how much electric power do you need. So you saw a shuttle launch when we started this presentation, right? How much power, electrical power, is in a shuttle launch? It's 2.5 million newtons of thrust, 500,000 pounds of thrust. This specific impulse number is 453 seconds. That's the units of it. How much is that in power? Well, you go and do the math. I don't expect you to do the math, but it turns out it's 5 gigawatts of power. So the shuttle generates 5 gigawatts of power. Now, for those of you who remember Back to the Future, that means we could do time travel, right? 2.7 gigawatts, Tom, what the heck? No, the way to think about it is that California actually uses 40 gigawatts peak power in the summer. So that's a lot of power. And what that means is electric propulsion will never be used to launch spacecraft off the Earth. It just takes too much power. You need so much thrust to overcome the pull of gravity at the Earth that it's just impractical. But if you can get an electric propulsion system out into space, where the gravity is just the sun and the Earth and the moon, and you're far enough away, then a little bit of energy, a little bit of power, and a little bit of thrust can really move your spacecraft around. And so you need 10 or 20 kilowatts. Now the question is, where do you get that power? Well, you get it from solar cells, solar arrays. You take them off of your roof and you put them on your spacecraft. It's the other way around. So this is an example. That's actually the Dawn spacecraft that's presently flying, and this is one of their wings, and it's about a 35-foot-long solar array that unfolds from the spacecraft after it's launched, and it collects sun power out when you're out in orbit, and that becomes the electrical power that is used to fly electric propulsion systems. And if you actually look at the Dawn spacecraft, I don't have any good pictures of that, but this is an artist's rendition. So there's a nice, relatively small spacecraft in the middle. There's an ion engine, and then there's these big wings, which are the solar cells, creating the power that's being used in order to do electric propulsion. Now, let's review a little bit about this difference in thrust. Here we go. Again, on a chemical rocket, what you can see is that when it starts, oh, good. Here's a chemical rocket starting off, and we're going to look at the thrust.
Start, 1, ignition, and liftoff of the Delta rocket carrying Gravity Probe B, testing for truth in the physics of our universe.
Lots of thrust, everything happens. All right. Now, a short time later, it's done. In other words, a chemical thruster runs for typically on the order of 30, 40, 50 seconds, and then it's done. It's an enormous amount of thrust right away. So what that means is that you're getting all of your impulse, your push, right away. So you're going right up to speed, and you're going very, very fast, and then you coast the rest of the way wherever you're going. If you're going to Mars, you're coasting, because all the acceleration is done in the first couple of minutes by this very high thrust system. Now, let's look at an electric propulsion system. So now we're going to do a video of what happens with electric propulsion. Not much. Electric propulsion systems, remember, have a force of 1/3 of an ounce, or 1/2 of an ounce, like a piece of paper. But the good news is that there's no drag in space, right? So what you're doing is you're taking something in space with no drag, just a lot of mass, a lot of inertia, and all you're doing is softly pushing on it. So it's going faster, and you're still pushing, and it's going faster, and it's going faster, and by the time it gets over here, it's going faster than the chemical rocket was. And so what actually happens is that if you're going far enough away, by the time you're getting out there, you're going so much faster that you actually get there quicker. You have to keep thrusting for long periods of time. And it was, when I was going to do this, I actually had a chair where you can actually push a chair and show how this whole thing works, but it fell off the stage, so I'm not doing that. A thruster has to run for, an ion thruster has to run for a long period of time, tens of thousands of hours, or in this case, years. The Dawn mission, the thruster is going to run for 5 years. The good news about that is that if you run it chemically, it would have taken 4 or 5 years to get there anyway, about 5 years. And with an ion propulsion system, it also takes you 4 or 5 years, but we use much less fuel. So that's the whole idea of electric propulsion. You're pushing softly, not very much, but there's no drag. So eventually you're going very, very fast. Oh, and I should remember, we just did a study of a mission to Saturn. And it was actually very interesting because we looked at using an electric propulsion system to get there and push this satellite to Saturn. Well, it turns out Saturn's a long way away, like way past the end of the stage there. And so the spacecraft was going faster and faster and faster, and it actually got so fast that when we got to Saturn, we couldn't stop. It was going too fast to stop. It would take too much fuel for us to actually brake and go into orbit. And so we actually had to stop thrusting with the electric propulsion system around Mars, throw that system off and coast the rest of the way because we were already fast enough. We couldn't go any faster and still be able to capture the orbit around Saturn. So this idea of thrusting softly but continuously for long periods of time, you can get some enormous velocities and get there even faster. The ion propulsion mission to Saturn was 3 years less time than the chemical option because it was going so fast at these periods after some period of time. All right. Now, I wrote a book last year on electric propulsion, and my wife has started to introduce me as a rocket scientist. Okay. It turns out that means that it doesn't take much to be called a rocket scientist. And so what I'm going to do now is I'm going to make all of you rocket scientists because the criteria seems to be if you understand how one of these things works, you're a rocket scientist. And in 2 minutes, you're all going to be experts. How does ion propulsion work? So you have a chamber. So it's a container. And on one side of this container, you have some grids, literally grids with holes in them. You have a propellant, like a tank of, in this case, it's gas, it's xenon. And you feed that propellant into this chamber. So there's neutral gas in the chamber. And now you put an electron emitter on this chamber. It's called a hollow cathode in this case, but it's called a thermionic electron emitter. It's a good red hot emitter, and it emits electrons. And you hook up a power supply, and you put a voltage between this cathode and the wall, and you draw electrons. So you're just drawing an electron current in this box. And those electrons hit the gas particles. So in this case, it's xenon. So electrons hit the xenon particles and knock electrons off and produce ions. So what you get is you get an ion, a xenon plus, and a couple of electrons. Well, these electrons, which here are pink, go to the wall, and the ions go to the grids. Now, if there's a voltage on those grids, the ions are accelerated. So all you do is just, I'll get to the voltage in a second. I already forgot. It's not very efficient to just run this discharge to the wall. And so what we do is we do very special geometries of magnetic fields and shapes and different configurations to make it very efficient. So only a little bit of electron current is needed to make all these ions. So this shows some magnets and some magnetic fields that are used in the geometry of making these types of thrusters. And then you put a voltage on the grids. So you made an ion, the ion's coming towards this grid. It sees this very high voltage, 1,000 volts, maybe 2,000 volts, and it's accelerated. That acceleration means the ion's going that way, so the rocket, the thruster, the spacecraft is going this way. And that's all that's involved. Well, almost all. There's only one more thing that's involved, and that is that if you're throwing ions out that way and you're going this way, that means you're leaving all these electrons around. If you're leaving electrons around, there's something called Gauss's law. And what it means is that you get more and more negative, and you charge. Your spacecraft is charging because you're throwing out all the positive charges and hanging on to all the negative ones. And literally, the spacecraft will start to arc and spark and throw lightning bolts because of all this negative charge. So you got to get rid of electrons too. And so what you do is you put a little cathode on the outside also, called a neutralizer cathode, and you just spew out a few electrons also. So you're shooting out an ion beam. You're also shooting out a few electrons, and you get rid of all this charge. Everything is stable and nice. You're all rocket scientists now. That's literally all that's done in an ion thruster. Now, of course, the engineering is way worse than that. So these are actually pictures of the Dawn hardware. The solar array I already showed you. The power from the solar array comes into these boxes, which are power conditioning units that turn it in from the 100 or 200 volts of the solar array into the 1,000 volts for the accelerator. And we have to run this electron discharge. We have to get these cathodes hot. There's all these different power supplies that are needed. That's all these power processing unit here. I mentioned there's a tank of xenon. You see it up there at the top. And below that is the control system so that the xenon gas goes where we want it to go and at the right rate. And then it goes to the thruster. But now the thruster also has a gimbal on it because you want to be able to point this thing a little bit. Remember the shuttle engines were moving around a little bit? They're gimbaled a little. Same thing with a rocket engine. You want to take this ion thruster and move it around a little bit. So there's a gimbal that you have to control. So the hardware is complicated. There's a lot of power supplies. There's a lot of controls for gases. There's a lot of parts and pieces. And so an ion thruster system that you see like this, it's got to work. It costs about $20 million. So it's rather expensive, but I have to tell you that if you were to launch this chemically, it would cost you $100 million to buy that big Hummer, that big launch vehicle. So it's still cheaper than doing it chemically, but it is a complicated system. So I showed you I showed you a schematic of an ion thruster, and of course it really does look like that. On the left-hand side, these are the magnetic fields I was talking about. These are actually the magnets. You see those magnetic field lines, and that's the ionized gas, and it's being held in by these magnets. A very efficient thing to do. This is a picture in my lab that I took about 2 months ago of an electron emitter. That's the cathode producing these electrons with xenon. So that's a cathode discharge. I mentioned we have these grids. I left my arrow out here for a reason. These grids are actually a bunch of small holes, and the ions go through these small holes and form these little beams where you can actually see them. These are the little tiny beams coming out of every single row of holes and forming the big beam that goes out. And on the right, you can see actually what ion thrusters look like. They're mostly grids and some type of a chamber. So I always tell people electric propulsion is a lot of fun because not only are you doing these, not as much fun maybe as chemical, now that I'm thinking about it. Those things blow up. But this is really fun because you get these beautiful glows and pictures, and you can actually go in and do diagnostics and understand where all these particles go. So it's a very interesting field. And it really looks like the drawings. Now, I thought I'd take just about 5 or 10 minutes and talk about the history of ion propulsion, because certainly we didn't do it first here. The very first research program in actually building hardware for flight was started in 1957, so over 50 years ago. And that was done at NASA Lewis Center, which is in Cleveland. It's called NASA Glenn now. And in 1959, JPL said, hey, maybe there's something to this electric propulsion, and they started a study group here on lab. In 1959, the first ion thruster at used cesium, which is a liquid metal, was operated by Ted Forrester. And the first mercury thruster, which is shown here, this is a mercury thruster, was operated at NASA Glenn by a guy named Kaufman. And then in 1962, JPL started its first ion propulsion laboratory, and that's actually now, 50 years later, that's my laboratory. So it's kind of nice. I inherited the very first one. Unfortunately, with the same old hardware in it. But now, the reason that I show this and even talk about it and give you names is that my thesis advisor was Ted Forrester. And Ted Forrester, he was a great guy. And he actually operated the first ion thruster in about 1957 or 58. And Kaufman operated these mercury thrusters a couple years later and published later. But Kaufman got all the credit in NASA for doing ion thrusters first. And so Forrester and Kaufman hated each other. I mean, they couldn't be in the same room. They were arguing all the time. They were saying nasty things about each other. And I actually met Kaufman a couple of years ago. He was a very nice man. But boy, these guys fought all the time. And I was trying to figure out why. And I talked to Forrester about it because I was a graduate student there. And I said, what's the deal with you and Kaufman? And Forrester said they were both professors. And he used a great line. I don't know if you've heard this one before, but he says, well, we're looking for who gets credit for starting ion thrusters. And you know, in academia, the battles are so fierce because the results don't really mean anything, right? It's all academic. And so I wanted to just show you. This is Ted Forrester. I look exactly the same, right? 30 years ago. This is me as a graduate student, and this is 1978, almost 31 years ago. And so I have a lot of history. Ted Forrester has the first ion engine ever made and flown. It's in the Smithsonian. Great guy. And Harold Kaufman, also a very smart guy. And together they flew the first ion thrusters. This is 1964. They actually flew a rocket called the Space Electric Rocket Test, CERT-1. So they actually flew a rocket into space, and they launched these two engines. The left engine is Forrester's cesium engine, and the right engine is Kaufman's mercury ion thruster. Now, the reason that that's kind of fun is that it turns out that, okay, Forrester did it first. You all heard me say that? Very loyal student. But it turns out that in this particular test, the feed system failed on the cesium one, and so Kaufman was actually the first thruster to operate in space of these ion thrusters. So maybe that's also some of the conflict between the two of them. But the following year, they ran it again, they did it again, and Forrester's worked. So, you know, there's plenty of credit to go around. NASA kept working on this. In 1970, they flew the second main satellite. It's called CERT-2. And in this case, remember, NASA flies NASA hardware, and the Kaufman thrusters were done in Cleveland at NASA Lewis Center, and so they flew Kaufman thrusters. And there's two of them. There's one there, and there's one up at the top on this particular spacecraft. And the idea was, okay, now we've shown that these thrusters work. Let's show that they run for a long time. Remember I said 5 years? Well, the goal in these tests was to run for 4,000 hours. And one thruster lasted almost 4,000 hours, and the second thruster only 3,000 hours, and they both failed. And so the performance was great. Good efficiency, the thrusts they wanted, everything was just fine, but the life was the issue. And 40 years later, that's the big issue in thrusters. What's the life of thrusters? How long do they last? How do you get them to run for 5 years? I just want to do one more quick thing about the history of this. In the 70s, they started to build bigger thrusters. This is actually it's 30 centimeters in diameter. That's about this big. The ones they flew earlier were like that. So this is 30 centimeters in diameter. It was actually built by industry, by Hughes Research Labs out here in Malibu. It was a 2 kilowatt to 5 kilowatt power level. You can see the grids on the front. And there were a couple issues with this. And the first issue is, where were they going to get 2,000 watts? In the 1970s and even into the 1980s, those big solar arrays were not available. And so even if they had an ion thruster, they didn't have enough power available to the spacecraft. And I actually went to Forrester and I said, what the heck were you thinking about? Why are you making big thrusters like this when there's no power available? And he said, oh, we were sure that by the 1980s there'd be nuclear reactors on every spacecraft. And if there's nuclear reactors flying, then who cares about a little bit of mercury spewing into the atmosphere, right? Because you got plutonium out there anyway. So there was a whole concept back then of you could use these exotic materials and you could use nuclear power and make electric propulsion. And of course, none of that came true. And so we had to wait a long period of time before we could really fly these to get the solar cell and the solar array technology. And the very first thruster that actually was flown to push around a satellite for real, the communication satellite, was done in 1998. And it used only 400 watts, the very first one. So it used the technology that was basically at the power level that they demonstrated in the early 60s, but they're just waiting for the spacecraft to get mature enough to be able to use it. And life was certainly an issue. Now, NASA, of course, got away from this nasty mercury stuff and designed and built the NSTAR thruster. It's their kind of state-of-the-art thrusters. It's actually flown on a Deep Space One mission. It's now flowing on Dawn. This is the Dawn spacecraft. And these are the solar arrays I was talking about folded up. And here's the NSTAR ion thruster here at the bottom. There's actually 3 of them. And so this is actually the state-of-the-art thruster as far as NASA is concerned. But how long does it last? Well, it turns out that when you look back at the life tests of all these thruster pieces, they had 65 life tests from 1961 to 1995. All of them failed. Every single one of them didn't meet the design life. And so JPL stepped up and said, look, if we're going to fly this thing, we need to understand life and really take this on as our responsibility and make these thrusters work for thousands of hours. And so we put in our own test facilities. Here's a picture of the large vacuum chamber, because we're simulating space. That's been pushed into this region here. And the reason for showing you this picture is you see that building, that's a block wall. That's that same block wall. The rocket engine was on the other side of that wall. So they did chemical stuff in this same building back in the 40s and 50s, and now we do electric propulsion stuff in it in the 90s and the 21st century. And if you look inside these big vacuum chambers, this is looking down the bore. That's the ion thruster at the end. These are these big panels. We actually coat them with graphite so they don't erode very fast. And we test these things for a long period of time. Now, the first N-STAR test was 8,000 hours, which was 1995. 8,000 hours is almost a year. And it actually successfully passed that test. That was the very first one that ever passed. And this is a fun picture because I think you can see here propulsion is still a dirty business. That's Dr. J. Polk, covered with graphite from working inside of this chamber. He doesn't look very happy, does he? But he ran this test. It was a very successful test. There were some issues that they found. They fixed them, and they started the next test, which was 30,000 hours. 30,000 hours is about 3.5 years, something on that order. And they ran it for that period of time, and they took it apart. It was still running just fine, and they found lots of things that were wearing out. And I was telling you there are ions inside this chamber. The ions go out and make thrust, but the ions also hit the pieces on the inside, and they erode it by sputtering. They hit the surface, and they sputter the material away. And so this erosion is mostly what the life-limiting issues are in a thruster. And you actually look, this is the electron emitter I was showing you the picture of. This is kind of the end view. At the end, it looked nice and beautiful here at the beginning of the test. At the end of the test, the front plate was eroded away. And actually, the cathode itself was severely damaged. And also the grids, which started out with a hole which is this big, at the end of the test, the hole was this big, and there's lots of other structure in the grids, all from this ion erosion. And that left a lot of material inside the thruster, which are all these flakes. And that's bad because flakes cause electrical shorts. We have thousands of volts, and you don't want flakes around. So there's lots of things to work on in order to improve the life of these thrusters, even after 30,000 hours. And we do that by modeling and testing. So you can make improvements, and then you got to run another life test. How long is it going to run? The 30,000 hour life test took us 5 years. Well, I want to run 50,000 hours. Well, that's going to take us 10 years. And I'll be honest with you, I don't have 10 years to sit around listening to the Blue Danube waltz, right? So the way we get around that is that we actually create very detailed models of these erosion processes. These are plasma physics models. They're done primarily by Dr. Michaelides in the back of the room there, and Ira Katz. And what they do is they actually find where all these particles are, and they find out where they're going to go. And this is an example. These are the grids that I was talking about. And you can actually break this into a calculation. These are trajectories of ions. And what you can see in this particular case, the ions hit the other grid, and they would erode it and sputter it away. But if you operate the thruster properly in the center one here, the ions miss the grids, and they leave, and there's no erosion. So this kind of tells us how to operate a thruster. And this are also examples of inside the electron emitter. What are the plasma parameters? It's a big word. What's the density? What's the temperature? What's the energy of the particles? We do all those calculations. We calculate all the erosion. We find out where the problems are. And then we go in and we fix the thruster. And then you start over again. Now, that works actually incredibly well, because we built a thruster based on these models. If we know where all the particles go, we know how to build a thruster. And that's the thruster you see on the upper left. And this is the one for that big 2005 mission to Jupiter, right? The big ion thruster one. This is a 25,000 watt ion thruster run by a nuclear reactor. It's this big in diameter. And you can see that I don't think it's a dirty business. I'm smiling, right? And I'm there with Tom Randolph, who's the program manager on that one. And it was the highest efficiency thruster ever. Over 90% of the power and over 92% of the fuel turned into the beam. So it's the highest efficiency ever made. So we built big thrusters based on our codes. And we also built small thrusters. And this is an example of a 3 centimeters. That's just a little over an inch. The thruster is only this big. And it only puts out a very, very small amount of thrust, 0.00 something ounces of thrust. But that's exactly what you would need if you're flying a small spacecraft and you're just doing a little bit of positioning and motioning, called precision formation flying. So big thrusters and small thrusters are all possible now because we have very good models and we understand where all these particles go. All right, now having said that, there's lots of different kinds of thrusters. And I started out this lecture thinking, I'm going to talk about different ways to do electric propulsion, and who has time for that, because ion thrusters are so much fun. There's lots of different ones with different characteristics. Arc jets, these Hall thrusters are actually a very popular thruster in Russia. That's this one here. That accelerate particles, there's a channel. It doesn't use grids. It uses electromagnetic fields to accelerate these particles. There's these very, very high-powered thrusters. This is 200,000 watts of a thruster, and it's running with liquid lithium in it. And also a pulse inductive thruster, megawatt level thrusters. So if we get nuclear reactors out there, there's lots of different thrusters that you can use. And there's even smaller thrusters. I was talking about this little 3 centimeter, 1 inch diameter thruster. Well, maybe there's even smaller ones that we have to do, and those are called colloid thrusters, which I'm going to get to in just a moment. I forgot I put this in. So let's take just a minute and talk about applications of ion thrusters, and then I'm going to show you this really, really small thrusters. It turns out that this whole idea of launching spacecraft into the solar system and using electric propulsion to get there works great. You can also do that around the Earth. So communication satellites around the Earth are held in position by electric propulsion. What actually happens is everyone has DirecTV, right? All of you wish you were watching the UCLA game with me right now on DirecTV. DirecTV uses what are called geostationary satellites. They're in orbit around the Earth, and they're stationary over wherever we are. That's at a given location. And the Earth's axis is tilted relative to the solar system. And these are on the equator. So they're going at this angle, all right? The sun is over here, and the spacecraft is going at this angle. So that means every time it's at this point, it's being pulled into the sun. And every time it's at this point, it's being pulled the other way. And so what actually happens is there's a lot of motion of this orbit. It's being tried to be pulled down into the orbit of the sun. That means it's no longer stationary. And you could push it back into position using electric propulsion. Now, historically, they did this with chemical rockets, and they would launch 5, 6, 7,000 pounds of fuel with a chemical rocket. And now, we actually launch about 300 pounds of xenon, and we do it with an electric propulsion system. And it costs about $10,000 for every pound of chemical fuel, or every pound of fuel you take into orbit. So if you're saving thousands of pounds of fuel, you're saving millions of dollars on every launch. Remember we talked about lower cost with running your Prius? Or what you can do instead, and this is an example. This is actually satellite radio. These are the thrusters right there. You can see them actually on the bottom of the spacecraft. This is stowed. Here's the solar array. Here are these thrusters. These are the Boeing satellites. Or what you can do with these thrusters, instead of actually saving the money, is instead go ahead and launch a bigger launch vehicle and take more channels with you. And so you can save, it turns out you can save $10 or $15 million on every launch by using electric propulsion. Or you can add 10 or 15 channels of DirecTV. Well, that's where you make all the money, right? More channels. So they actually make these very big satellites to do hundreds of channels of DirecTV and satellite radio using electric propulsion. And as a matter of fact, electric propulsion is used in, this is a chart from Aerojet, but there are 226 satellites orbiting the Earth right now that use electric propulsion to position themselves. So it's a very, very common application around the Earth. And the reason is that around the Earth, if the thruster lasts for like 10,000 hours, that's long enough. And the thrusters we have now, you saw the N-Star thruster lasted 30,000 hours. We can do that. It's the thrusters that are going for deep space that are hard, 50,000, 60,000 hours. And that's why we still have a program here at JPL, is to get even more life out of these thrusters for deep space missions. And I showed you this facility that we do for life testing here at JPL. That was actually borrowed from a national laboratory, kind of old hardware we kind of klooched together. Out in industry, of course, it's communication satellites. DirecTV makes a lot of money, and so their life test facilities are spectacularly beautiful. This is actually down at Boeing in Torrance. That's where we did the enormous life test a few years ago, showing that the thrusters lasted long enough. Very, very beautiful. You can eat off the floor. It's really nice. Anyway. Finally, I'm almost done, but I wanted to talk about this very, very small thrusters. So I talked about big ones for pushing around satellites and getting to Saturn, but there's other missions out there, and they're astrophysical missions. This is one where what they want to do is they want to measure gravity waves. Gravity waves are predicted by Einstein's theory of relativity, saying that the space is going to bend on these waves associated with gravity. And if you put what's called an interferometer, which is an optical method for measuring displacements out in space, you can actually detect these waves, because one will move and the other one won't, and you'll be able to see that these gravity waves exist and prove Einstein is right, which apparently everyone likes to do. In order to do this, it turns out you have to position spacecraft 5 million kilometers apart, right? Millions of miles apart. And you have to hold them in that position to 10 to the minus 9 meters. Right? A meter's this big. So 10 to the minus 9 meters is really small. Now, you would think you could, I said there's no drag in space, right? Okay, that's true. But there's also lots of stuff going on in space. There's light from the sun. That's pressure. The photons from the sun put pressure, and they can push spacecraft around very slowly. Certainly enough to move 10 to the minus 9 meters. And also the solar wind is actually electrons and charged particles, and that also moves spacecraft around. So to hold these satellites in position for this interferometer to work takes about 10 to the minus 5 pounds of thrust. It's the weight of a mosquito. And the precision to hold it in that position is the weight of the whisker of the mosquito, 0.1 micronewtons. Now, how do you do that? Well, we use inkjet printers. The way an inkjet printer works is ink is a conducting fluid. So you wick ink through a needle. You put in the same grids that I use in my ion thrusters, and you accelerate those charged particles, and you form a beam. It's a very small beam, and it has a very, very small amount of thrust, micronewtons. But it's exactly what's required for this type of an application. So what you can see is that electric propulsion spans from thrust on the order of very small compared to a mosquito, up to thrust, which is on some fraction of a pound, for positioning spacecraft or for moving it in the solar system. Whoops, back up one. So people are using these for different applications. I just wanted to mention NASA isn't the only one. These are international missions. This one up here, they sent the SMART spacecraft. ESA, the European Society, sent this spacecraft to the moon using electric propulsion. This is the Japanese sent a spacecraft to an asteroid. They actually tried to pick up a sample and bring it home. The spacecraft is on the way home. They're not sure they got the sample, but we'll find out. And pretty soon, the Europeans are going to go to Mercury using an ion propulsion system. That actually, interestingly enough, they're coming to JPL and asking us for help to make it last long enough, to have enough life. Because of our modeling and testing capability, we're actually the experts in making them last long enough. So finally, to finish up, electric propulsion is really a great thing for lots of missions. If you wanted to do things like go to an asteroid or to a comet and pick up a sample and bring it back, well, you can do that with electric propulsion way better than you can do it with a chemical system, because the spacecraft is small enough that it can be easily launched. It motors around the solar system, and then it motors back and can be recovered. The same is true for actually landing on the spacecraft. These are sample returns. These are just rendezvous looking at them. So these are applications of electric propulsion. The mission, or this picture on the right I'm showing you is, remember I talked about that one that went to Saturn that went too fast? That's the spacecraft. Big solar cells, run around, head for Saturn, but stop thrusting near Mars so you don't go too fast. And the one on the top is I just wanted to mention is that we still do chemical propulsion. This is if we went to Mars to bring the samples back. You land on Mars, you have to have a rocket to get off of Mars to come back. Well, so we still would do those types of chemical missions. But I'll be honest with you, my point of view is once you're outside the orbit of Mars and you're away from all that gravity, use electric propulsion to get back. Because that's a lot better. So let's just hope that the missions in the future are electric propulsion, because not only is it really a great job, everyone in the room is going to buy a Prius these days, right? And we're hoping that most of the missions that are coming up in the future are electric propulsion missions. Thank you. So questions? You're all rocket scientists now. You know exactly how to do this. Sure, please.
Okay, I have a question about the different fuels. I think I remember cesium's easy ionized, mercury had multiple ionizations, xenon. Could you say something about the different fuels for ion propulsion, and if you think that the best one is yet to be found?
Oh yeah, it turns out that the way that it works actually is you're throwing an ion out there. Well, the bigger the ion is, the more thrust it is, right? The bigger the bowling ball going that way, the more pressure is pushing the spacecraft this way. So you want to use something very, very large. Cesium, mercury, xenon, they're all really big atoms, so they give you this same amount of thrust. The liquid metals you mentioned, you were right. Those are easy to ionize, so they made very efficient thrusters, but they're caustic and nasty stuff, so we don't want to use them. Xenon is really great. Anything else that's radon would be super, but it's radioactive. You know, so for right now, xenon looks really good. We haven't found much else. Yes?
I have a question about when you're like the SMART mission that went to Moon, and it's taking a long time to get there by going many orbits of the Earth.
Yes.
Is it possible that it takes more delta V when you go slowly like that than if you did it all of a sudden in one?
That's absolutely right. And on the average, it takes almost twice as much delta V in order to go slowly and spiral out like that. So there's a penalty for using electric propulsion because it takes you a long time and the orbit is not optimal. So chemical is a little bit more efficient on that, but it turns out you still win because the ISP is much larger than that factor of 2. Right. We do ISPs of thousands of seconds instead of just hundreds.
I have one other question. If
Sure.
if you're going to say some place like Mars, I saw a paper once where they talked about adjusting the thrust to minimize the time to get there. You sort of have like different gears, and
Yes.
when you start off in a low gear, a low ISP, and then you end up with a high gear and a high ISP, and that for a given amount of fuel, you can get there in less time. But
He is a
that's-
rocket scientist. That's exactly right.
Okay. But is that something you ever want to do with an ion engine?
Yeah, it turns out that you do want to do that. That's called variable ISP operation, and that's what we're trying to do now is change the range over of ISP that our thruster will run at, so you can do more, more thrust when you need it, more miles per gallon later on when you need it at different locations, and that's part of our research and development effort. Absolutely. Yes.
Are these meant to like replace the chemical thing, like propulsions?
Yeah, it turns out not for launching off of the Earth because it just takes too much force, too much thrust. But once you're out in the solar system and the gravity is small, then it's meant to replace chemical rockets with these electric ones. Yes.
Cool.
And you save a lot of money or you deliver a lot of mass. Those are the good things. Exactly.
Well, first a brief comment before my question. Aerojet General was the JPL spinoff that von Karman founded to make JATO rockets for the jet assisted takeoff for over
In the 40s, yes.
Yes, and Aerojet General is still there. It's a JPL spinoff. The question I had was you mentioned that the thrusters operate with a potential of something like 1,000 to 2,000 volts on the grid. Is there a trade-off between the voltage, which would give you greater acceleration, and the damage that the ions do to the grid?
Absolutely, that's a major trade-off. And what we find is that higher and higher voltage, higher ISP ion thrusters erode faster. And so we have to do a much better job in calculating where they go and make sure that those particles don't hit anything, minimize the ions that do hit the grid. So it's much more challenging to get very, very high ISPs.
Thank you.
That's why we do models. Models are great for that. Yes?
Other than Dawn, have there been any major space missions that use ion or electric engines?
Well, before Dawn, there was something called Deep Space One, and you heard about that one.
Yeah.
And that's for NASA. That's it.
I watched the impact online. That was neat.
Oh, okay, good.
Yeah.
Yeah, and so we're hoping for another one coming up in another few years. So, and the next one I think that's the Europeans just launched something called GOCHI, and that's a Earth measuring things in Earth, and it has ion thrusters on it for positioning that spacecraft in orbit. We're hoping more and more. Everybody should love this. I do.
Speaking of fun with rockets, you mentioned the occasional tendency of chemical rockets to blow up and cause a little excitement. A few thousand volts, do you ever get at least a few sparks flying around?
Actually, you do, and it was a funny thing when I first started working in this field. I said, occasionally these things just kind of arc and spark a little bit. What do? It turns out you build your power supply to just sense that. You turn the power supply off for about 1 second, turn it back on again. The arc goes out and you just keep going. It's called a recycle, and it's very standard, and right now, ion thrusters recycle maybe like once a day. A little tiny arc or a little spark hits. Yeah. It sounds like a lot of voltage. It is. Yes?
With the ion thrusters and the improved ISP, like if we're talking about like deep space missions, like out maybe to the Kuiper Belt and past, like how long are we talking about? Like how long, like relative to traditional chemical engines, like how much improvement?
Actually, it turns out that if you're going way out like that, and you have power to thrust, you can't use solar cells, you have to have a nuclear reactor or so, you can go faster and faster and faster. So the time that it takes to get to the very far outer planets is a half or a quarter or a third or something, what you would get in a chemical system. And how long is that? Well, it's 5 or 6 years to get to Saturn, so maybe out to Pluto is 8 or 9 years, and into the Kuiper Belt's even longer than that. So it's a long time. So if you start early when you're in your graduate career, you can see it before you retire. So, Yeah, electric propulsion has been around, as a serious thing for certainly 50 years now, and it's only been flown significantly in the last 10 years, but it's growing enormously because of those benefits. And so people that are starting electric propulsion missions now say that they are going to actually fly in 5 or 10 years from now rather than before they actually, or after they retire.
Well, it took 50 years to get where you are right now. What do you expect in the next 50 years?
Oh, good, actually. It turns out that there's a lot of, well, what we're doing is we're working on making better electric propulsion thrusters, right? Which means higher efficiency, more thrust, variable ISP is a very good one. So it kind of tweaks on that. And then the other thing is I showed all those different types of ion thrusters. The idea is that if you really want to use electricity, you have to have a source. So if we can find a source for higher electricity, higher amounts of electricity out in deep space, then we can go to these very, very high power rockets, electric rockets. And those have very short life. That 200 kilowatt one that I was showing you there, that's like 50 hours. So there's all this work to be done for very, very high powers, and that's the next wave of work that's coming forward. Very high power or very low power.
You also mentioned that universities played a major role in the development, not only JPL.
That's right.
What are the universities, which universities and which one have programs right now?
Well, I'll just, yes, it turns out that a recent graduate of Caltech who worked here at JPL for about 3 or 4 years is now a professor at UCLA. So UCLA has a program again. It stopped when I left and Ted Forrester retired back in the 80s. UCLA is starting again with electric propulsion. Stanford has a program, University of Michigan, Princeton, Georgia Tech. I apologize if I'm forgetting MIT. So most of the major universities have research in this area. Part of the reason is the facilities are pretty large. You need these big vacuum systems, and you have to have a pretty good-sized university to support the operating and testing of them. And you have to have pretty good students because the models are pretty complex. But the big ones are, there's 4 or 5 out there. Yes?
Do you think electric propulsion will ever be used for manned missions?
Yes, because never say never. The challenge for manned missions and I've actually seen some of these studies and worked on them, is that you need a lot of power. You have to be able to get a half a megawatt or a megawatt of power and run these relatively high thrust engines, because you can't take 5 or 6 years if you have a manned mission. You have to do it in months. And so that means you need a lot of thrust. So if you have a power source, then you could use an electric propulsion system. And so I think as we come up with ways to create this power, whatever that little battery pack is in the phaser, that's what we want. Something that has a lot of power, and then you'll see it used for manned missions, because then you can use these special systems and really get a lot of thrust out of an electric system. That'll happen. Good topic for your thesis research. Yes?
Like in 50 years, you got from like chemical thrusters to these electric ones. Do you think that you'll get like the same amount of stuff done in the next 50 years?
I sure hope so. That would be great. Like I said, there's lots of candidates out there. We understand the physics of these devices pretty well, and there's lots of good things to work on. So we can make a lot of progress in how long they last and how well they work. So yeah, I think there'll be a lot of progress. Part of the delay in the last 50 years is just waiting for the solar cells to get big enough so we could actually have enough electricity. If we have enough electricity, you'll see big advances coming through in the future. Yep. All right? Oh, good.
So
One more. Thanks.
what other technologies might interface with this technology, and what would that produce? What other uses could it be put to?
Oh, what other uses? Well, certainly not NASA uses, honestly, is that the technology is, ion thrusters are ion thrusters. But the same types of technologies are used in a lot of industrial applications here. It turns out that they used to make, you heard earlier that I invented the machine that makes sunglasses. Well, that's a plasma source, an ionized gas source. It uses a cathode and a discharge chamber similar to this, and it produces, it sputters material. The same thing that wears out thrusters throws that material on the sunglasses, and that creates the the different layers that cause different index of refractions and attenuation in your sunglasses. So the point is that same technology is used in a lot of things. We use it in semiconductor processing. We use it in making coatings on sunglasses, on windows, on parts and pieces for the medical profession. Anytime you have a situation where what you're looking for is energetic particles, this technology is really good at that. You can accelerate the particles, give them a little bit more energy, and then deposit them or sputter with them, and it's very, very useful. So it's very common in the industrial applications. Not so common now for NASA, but we're hoping more and more. Thanks. So I know my time's almost up, but I just wanted to mention is that, okay, I invented this device. We actually spun off from my laboratory at UCLA this company to coat sunglasses and licensed the technology to a company in Germany. The company has made, I believe, $700 or $800 million selling machines based on my little plasma source. It turns out sunglasses are $1 to $2 billion a year of business, and so they've sold about $15 billion worth of sunglasses. And I'm the inventor of the basic device that made this possible, and I have a really nice BMW. And the reason is that, doing this type of work, this is research and development, it's doing the scientific research and the modeling, it's really fun and interesting. And for me, it's way more interesting than making money. And so I think I'll always have a job doing these types of things because it's fun and I enjoy it. And hopefully, people that are just interested in making money are now being fired by AEG and those types of things, right? So even though they were rich, they're going to get their own. And us, scientists and engineers, we're always going to be very interested and very satisfied with our work. I really enjoy this and I really like doing it. I'm glad I had a chance to talk to you about it. Thank you.